Hey, this is the video for 4.5, Global Wind Patterns. So go ahead and check out the overview and set up your guided notes. So we are going to discuss convection currents. And convection currents, remember, are when you have movement from basically hot to cold through a fluid. And this fluid is the atmosphere, the gases in the atmosphere. And most notably, we're talking about the troposphere. So this is not to scale by any means, but just this is drawn or done to show you how everything works. So remember that most of the sun's energy, or a high percentage of the sun's energy, are hitting directly onto the equator. So this will be the warmest place in general year round. And what happens is this air heats up, and when air heats up, warm air is less dense. So the warm surface area is going to rise, and that's indicated by these arrows with the red. The air is going to cool and then hold less moisture. So when it cools, it holds less moisture and it falls back as rain. That is why we have a majority of the rainforests found on Earth are found at the equator. Because this is getting a lot of solar energy, the air is rising, then it's cooling and losing its moisture, and then that water is falling right back down where it came from. Now the cool, dry air is going to sink, and this is going to sink because it can't, by the way, it can't move up any further because it hits the tropopause, so it's going to split out. Some of it's going to go in the southern hemisphere, some is going to go in the northern hemisphere, and then it's just going to continue to cool as it moves north of the equator and south of the equator. And the cooler, denser, drier air is going to sink at 30 degrees north and 30 degrees south latitude. And that's why we find a lot of deserts at this latitude. So the air is then going to return back. The air currents are going to return it back to the equator, where this process will continue. Now the next area is we're going to have some of this low pressure air is going to rise at 60 degrees latitude, northern and southern hemisphere, and then it's going to cool and sink at 30 degrees latitude. So now we have two situations where the cool air or the dry air is sinking at 30 degrees, which also explains why we have these deserts. And then finally, what we're going to have is we're also going to have this dense air falling from the north and the south pole. And this air doesn't mix well with the other layers, so it is going to form its own little convection current. Now, all of the currents together, you notice that they are all basically either convergent or divergent. These two are moving apart, these two are coming together, moving apart, and the other side will be coming together. Now, why is this important? Well, this is important for if you ever have to figure this out on your own, and we'll be talking about this during class. But this first cell, the Hadley cell, is found in the tropical areas north and south of the equator. The Ferrel cell is the convection current, the atmospheric cell that is found in the area that we live. And the polar cell is found near the north and the south pole. So if you look at these currents globally, this is the equator of the Earth. We're 30 degrees north, 60 degrees north. This is showing you the directions. So this is these two are the Hadley cells. This is the Ferrel cell right here. This is a Ferrel cell. And these two are the polar cells. And as the same on the bottom, or the southern hemisphere. If you notice the arrows are going down, going towards the poles. Okay, and everything else is moving basically opposite. Now, why is this? Well, on the surface of the Earth, the wind patterns are due to the Coriolis effect. And the Coriolis effect is just a deflection because of the rotation of the Earth on its axis. So it is going to deflect this way in the northern hemisphere and this way in the southern hemisphere. Of course, you're going to see this because we're doing a lab that is based on this phenomenon. Now, in the Hadley cell, we're going to have the trade winds are going to blow towards the equator from the north and from the south, and they really rarely will cross the equator because they're basically converging right here and blowing from east to west. In the next cell, in the Ferrel cell, they're going to be flowing the opposite direction, but with the same deflection. And finally, in the polar regions, they're going to be flowing in the same deflection, but they're going to be converging at this area. Now, do you have to know all of this stuff? Not really. You should really focus on the direction of the winds in the Hadley cell. Now, what does this matter? Why do we care? Well, if you look at a typical Atlantic hurricane season, the equator somewhere around here, and you're going to have the hurricanes. If you look at the path of the hurricane, this just represents different hurricanes or tropical storms throughout an active hurricane season. Now, this is an approximation, but if you notice, they're all kind of starting over here in the northern hemisphere. They're blowing to the west, and then they're shooting up. So this area right up here is where we would have the Ferrel cells. This area down here is where we have the Hadley cells. What I would like you to do is respond to this check for understanding. And finally, I want you to justify the typical latitude of deserts around the Earth. I hope that this video was informative. I thank you for your attention, and I will see you soon.